Okay, guys, so let's take a look at our chapter 3 homework. So we're going to go over to assignments in MyLab. And let's take a look at chapter 3. So to remind you, in case you didn't watch the first 2 videos, notice that looking at these videos that are in here and reading the textbook are all worth a point on the homework. So you have to do all 3 of these links first, and this one down here after you pass question 5, before you can get full credit on the homework. So make sure you click on all of these links on the left-hand side to view those videos. But then the actual homework problems are here on the right. Let's take a look at some of them. Okay, so the accompanying data provide the carbohydrate content in grams of 77 breakfast cereals. The histogram displays the data. We want to describe the distribution. So let's look at the histogram. And notice what we have in this histogram. It looks like there's one large peak here, but there's also kind of another peak right around here. It's not quite as big as the other, but if I were to like draw over this, notice that I would be drawing something that looked a little bit like that, right? Kinds of, well, this needs to come down a little bit more, right? But it kind of makes 2 peaks to that data. So it looks like there may be the 2 groups of cereal that are going on there. So let's try that. Whoop. Let's try that again. Let's look at that histogram again. It's, well, okay, so we're not going to, so I guess because there is a large gap there, we wouldn't quite categorize that as 2 different, but I can definitely see a drop down here and again. So it looks like this is, they're wanting unimodal just because that is the one largest peak. And there doesn't seem to be any outliers. Let's look at the actual raw data that's here. And we don't see, notice everything's going between those 5 and 25 values, I think was the highest, something like that. So we don't see anything that, or 26 here. We don't see anything that's hugely different in between those 2. It's just simply spanning that realm. So let's try with unimodal. Oh, wait, I'm sorry. I didn't see this as a select all that applies. So that will get rid of that. There shouldn't be any outliers. We have 2 groups of cereals and no outliers. Okay, good. I was hoping they weren't saying that was unimodal because again, if we look at that histogram, there are sort of 2 peaks to that data. I just didn't see that that was a select all that applies. Okay. So we have another select all that applies. Identify the 5 cereal brands with the highest carbohydrate count. For this, we have to look at the actual data. So our highest count was around that 26. So brand 77, brand 73, brand 74. So let's mark this. Brand 77, 74, 73. So 77, 74, 73. Okay, so we need 2 more. So this was 24, was that high? So I see this 23 here at 62. Now notice how cumbersome this is to actually sort through the data. When you have a lot of data points, it's going to help if you can sort the data. So if we could export this to another function, that would be great. So it looks like that 62 is my next one, 23. And then after 23, I wonder if 21 is my next. Let me see. There are multiple 21s. Oh, there's a 22, number 16. Okay, so number 16 and the 23, which was 62. 62 and 16 we should be marking. So 16 and 62. All right, now this histogram shows the sizes in acres of 44 vineyards. Approximately what percentage of these vineyards are under 60 acres? Let's look at this in a bigger. Now, notice this is the number of vineyards plotted here. So that means that I have 14 vineyards that go between 0 and 30 acres. I would have 12 that go between 30 and 60 acres. So it asked me what percentage of these are under 60. So under 60 would be here. So we see there are 12 plus 14, that's 26. Now, I need to know what is that 26 out of? So I need to add up all of these other ones. Well, we know this was 26, and then this is 8 more, so 34, and then 39, and then 42, 43, 44. So I'm looking at 26 divided by 44. So if I put 26 divided by 44 into my calculator, I'm going to come up with, I guess I forgot to bring up my calculator, so I might have to bring that up for a future screen, but I'll just use my handheld calculator for right now. 26 divided by 44 gives me 59.09. So I want to go to the nearest percent, so that would be 59%. Describe the distribution, shape, center, spread, unusual features. Now, again, if I pull this back up, notice that this seems to have like a peak here and goes down. So again, if I draw over it, my curve would look sort of like that. This is not uniform. This is, right, uniform would mean it's kind of all the same all the way across. That's what we mean by a uniform distribution. It is unimodal because there's one big peak here. It's not bimodal. There's not a second peak to the data. So we're going to pick unimodal here. Is the distribution symmetric or skewed? So notice that we did not see like the same on both sides. Remember we talked about in the video, symmetric would be like where it does something like that. It's the same on both sides. This one did this, so that is skewed. And notice you have items pulling to the right there. So we are skewed right. Which of the following best describes the center? Now, in the video, remember we said that the symmetric is best described by the mean, but when it's skewed, it's best described by the median. So the center is best described by the median, that's either A or C, but it's skewed to the right, so we're going to choose A. What is the spread? So now if we look at the spread, that's how many acres we're going from. That's 0 acreage to 270 acres. That's our span. Describe any unusual features. Most of the vineyards have close to the same number of acres. There's one vineyard that has considerably more acres than the rest. There are no unusual features. Most of the acreage is here. And then we have this one weird one that's over here with a large number of acres, right? So we want to choose that there's one that has considerably more than the others. The accompanying histogram shows the lengths of hospital stays in days for all female patients admitted to a certain hospital during 1 year with a primary diagnosis of acute myocardial infarction or heart attack. Okay, from the histogram, determine whether the mean or median is larger. Okay, think about what we just said for the previous problem. If it's symmetric, the mean's a good description of center. But we use the median when it's skewed because the mean is affected by outliers. All right, so let's look at this. Here is our diagram, and we can see like a little bit of, if we draw the distribution of it, right? It would look kind of like that. So we're kind of pulling on this tail to the right a little bit, which means that my mean is going to be a little bit higher than the median in this case, because we have more data that's kind of pulling it to the right a little bit there. So let's see. This is the number of female patients. That out so we can see a little bit bigger. Okay, so let me clear that drawing. Okay, so we can see the number of female patients here that came in with the infarction and the number of days that they were in the hospital plotted along here. So it looks like my mean number of days, probably my balance point is going to be somewhere right around here-ish. I'll say, now that we can see a little bit better. Somewhere right around here, drawing, is where the two sides would sort of be balanced a little bit. That's what the mean does. It sort of balances things off. And the median, right, is the middle number. So if we look at like counting up how many cases we have, so I could approximate, notice that this is about where 500 is right here. So this may be like 480 cases, and this would be, that would be about 100. So maybe about 150. So if I keep adding all the way across, where the halfway, the middle point is where my median value would be. All right, so let's go ahead. So the distribution is skewed a little bit. To the high end, the mean is expected to be, the mean is about the same. The mean is expected to be larger than the median by just, in this case, probably not too much, right? But that was the original picture that I showed you there. All right. Now write a few sentences describing this distribution. So when we look at this, here it is again. Notice there's kind of like this one big peak in here where we have a large bulk of the data. So I would say that this is definitely not bimodal. It's definitely not uniform. So probably, I'm going to go with unimodal, although we could kind of say there's a little bit of a dip in there. So we could kind of draw like two modes in here where we go like this, right? So it's a little bit bimodal. So let's go ahead and try bimodal first. It's not multimodal. It's not really uniform. We're either going to classify this as bimodal or unimodal. It looks a little bit more bimodal from the way that we drew that in. And the center of the histogram. So we want to know approximately where the center of this histogram is. So let's pop it out a little bit bigger. Okay, so again, notice that I said our balancing point is probably somewhere right about here-ish. That looks like that's at day 6, 7, somewhere right in around that area is where I'd estimate. So now look at my choices. My choices are day 1, which is here, that's not good. Day 5, that's too early. Day 15, that's much too late. So day 8, that's pretty close to where I said it was. So our closest choice here is going to be day 8. Nope, not day 8. Let's try that again. Let me look at it. So our center must be a little bit closer to day 5 then because of this front loading. Because we've got a number of cases up here, so these cases must be really small. So let's see, 100. This is all less than 100 that are being added together. So because of the large number here and here, our median value, which is the one that we should use since this is not symmetric. So our mean is over here closer to that 7, but our median is closer to that 5. So we should be choosing day 5. What's the spread? So we said that the spread, notice we're going from 1 day in the hospital to 15 days in the hospital as the scaling. So we're ranging from 1 to 15 days. And what about the features? So there's a peak at day 1, right? And there's some data values are significant. So let's go back. Move this over to the side. Okay. Let me move this over to the side. There we go. All right. So there are many outliers. No, not really. Nothing's staying hugely far away from the data. Notice it's all kind of bulked together in between 1 and 15. There's a peak at day 1, which may represent patients who did not survive. Okay, well, it is true that there is a peak at day 1. So yeah, it may be that we did not have, because we are talking about people that came in with a heart attack, it would probably be a little bit unusual for them to stay only 1 day. So that may be the patients that didn't survive. Some of the data values are significantly different from the other data. No, notice that there's nothing that's extremely unusual here. It's all kind of similar. There are no unusual features for this distribution. Well, there are the 2 separate peaks, because remember we classified this as bimodal. So we're going to say option B here. Which summary statistics should be chosen to summarize the center and spread of the data? Well, we already said that the median is going to be a better measure of center. And we use mean and standard deviation together. We use median with the interquartile range since the distribution is skewed. All right, how many points do teams score in the championship game of a certain sport? The total numbers of points scored by both teams in each of the first 46 championship games are shown below. We want the median. So let's see if we can get this data open in Excel. And there it is. Now, there are a couple of ways that I can find this median. So the two ways that I could do it. Number one, I could go right over here to the data and I could sort my data. That's what I'm looking for. Oh, there it is, right in front of me. So I just highlight and then sort A to Z, highlight the whole thing, sort it. And we remember that the median is the data value in the center if there's an odd number, or it would be the average of the two in the center if it's an even number. But a faster way to do this is to let Excel do it for us. So there are two ways we could do it. We could either do number one, the median command. So I just list the values that are in there. So we're going A1 through A46. And it tells me that median is 44.5. Okay. The other way I could do that is to use my data analysis that's right here. And I'll talk about using this tool a little bit more as we go into further data analysis. But for right now, let's go ahead and return and put in that 44.5. Find the quartiles. Okay. Now for this, in Excel, I am going to go ahead and sort. Smallest to largest. So notice that there are 46 values. So half of 46 is 23, right? So we averaged the 23 and the 24th together to make the median value of 44.5. So what I did there is I actually said (44) plus 45 and divided by 2, and that's how we came up with the 44.5 for the. Now what that does is that divides the data into two sections, right? These are the lower half, and these are the upper half, other way around. These are the lower half, these are the upper half. So there are 23 data points up here. So that would be the 12th data point that would be in the middle. So let's scroll up. Let's scroll up. Our 12th data point is 36. So notice that leaves 11 here and then 11 more here before we hit that median value. So 36 is our lower quartile. Now the upper quartile, we come over here and at 23, same thing. We want to move up 11 units, and then the 12th one is the upper quartile. So 24 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the 12th one is 54. Notice that that's the same as adding 11 or adding 12 to the 23 where we started. So 54 should be my upper quartile. Are there any outliers? Okay. To do the outliers, I need to calculate my interquartile range. So my interquartile range is that upper, let me go back. The upper quartile, which is 54 minus the lower quartile, 36. And 54 minus 36 is 18, I think, right? So 18 is my interquartile range. Now, to determine if I have an outlier, we said we multiply 1.5 times the interquartile range. So 1.5 times 18 would be 27. So I take 27 away from the lower quartile. And I get 9, I think. So if there are any data values below 9, and then the upper quartile, 54, I add 27 to. And we get 81. So we want to see, are there any data values that are less than 9 or bigger than 81? Less than 9, nope. Bigger than 81, nope. So this data set has no outliers. All right, so none of the values fall outside these fences, so there are no outliers. So our upper fence is at the 81, and the lower fence is the 9. So we're going to fill all that in. All right, now do our box plot. So notice that we go to the data values that are inside the fence. So 21 and 77 are our biggest. So 21, 21, 21, 21. It looks like they're all starting at 21. These look a little closer to 20. And then 77, they're all ending at 77. Now we're going to place our median in the middle, right? 44.5. So I want to find, this is not at 44.5, so I can rule out A. This is not at 44.5, but these two both look like they're probably at about 44. Well, let me count. 40, 45, 50, 50, nope. So 40 to 60. And there are 1, 2, 3, 4, 5 tick marks in there. So each tick mark is 4. So this would be 44, this would be 48. So it looks like that median is too far over. Whereas this one, it's hitting right at the 44.5. Now let's check our lower quartiles and make sure D looks right. 36 and 54. So 36, yep, that's lining up. 54, yep, that seems to be about lining up. So we're going to select D. Write a description of the distribution based on the box plot and 5-number summary. So our lowest value is that 21. The first quartile was at 36. Yeah, 36. The median was at 445, 44.5. And then the higher one was at 54. And then our top value is at 77. So that's our 5-number summary. In the championship games, teams typically score a total of about the middle value, 44.5 points, with half the games totaling more than. So now, the box covers the middle 50% of the data. So it's going to be between 36 and 54. So they're going to cover more than 36 points, but less than 54 points. In only 1/4 of the games have the team scored fewer than, okay, so this is 1/4, 1/4, 1/4, and 1/4. So only 1/4 of the games have we scored fewer than 36 points. And the most the teams ever totaled was 77 points. A government bureau keeps track of the number of adoptions in particular regions. Given are the histogram and box plot of the distribution of adoptions. What features of the distribution can you see in both the histograms and the box plot? Okay, another select all that applies. I gotta be careful. Okay. Notice this kind of seems to be unimodal, right? There seems to be one big peak here. Kind of see that here as well. But I can't really see that in the box plot. I can't see that much at all. I can just see in the histogram that over here in the box plot, it doesn't jump out at me the same way. All right, now there are no data values between 4,000 and 5,000. I can see that here in the histogram. I can also see that here in the box plot. So let's definitely select that one. There are no data values between 2,400 and 2,800. Okay, I can see that we're missing it there. 24 and 28, I can see we're missing it there. So I can see that in both distributions. There are 4 potential outliers. Well, 1, 2, 3, 4, or 1, 2, 3, 4. Yeah, I can kind of see that in the histogram. I can definitely see it in the box plot. Notice it's a little bit harder to see in the histogram, but if we're looking for it, we can kind of see that there. The distribution is symmetric. No, I don't see that in either one. Skewed to the left. Well, notice that these are tailing to the right, right? And I can see that here, and I can see that by the outliers here and the longer arm here. So I'm going to say skewed to the right. So not symmetric, not skewed to the left. The mean, I can't see the mean in the box plot. It doesn't look necessarily bimodal, and I can't see a unimodal in both. What features of the distribution can you see in the histogram that you could not see in the box plot? That was where we saw that it seems to be unimodal. Now, can we see the mean? Let's look at that. It's kind of hard to make out where the mean would be, but we could kind of estimate it a little bit from the histogram. So from the histogram, we see that our balancing point is going to be somewhere over here. So I could estimate that mean, but the software may or may not want me to do that. Let me see. Yeah, so it doesn't like the mean estimation. So just we can see that it's unimodal. So that's probably a little low for the mean. I was trying to visualize it, but yeah, we're just guessing there. What summary statistic would you choose to summarize the center of this distribution? We would use the median. Why? Because the distribution is not symmetric with at least one potential outlier. What summary statistic would you choose to summarize the spread of the distribution? Now remember, the spread is how many values we're looking at, right? So we want to look at this spread here. So it's asking, would I use IQR, would I use range, or standard deviation? The spread of the data is always the range, right? And it actually doesn't matter here, but in this case, we're going to say not symmetric with at least one potential outlier. Oh, okay, I'm sorry. I didn't read this carefully. All right, so I would want to use the IQR. Let's look at why. If I go here. In the box plot, you can see that the range is deceptive. The range is the total spread of the data, but these outliers don't describe the bulk of the data. So the interquartile range would describe the majority of the data. Okay. For each lettered part, A through C, examine the two given sets of numbers Without doing any calculations, decide which set has the larger standard deviation and explain why. Then check by finding the standard deviation by hand. Okay, so if I look at set 1, 5, 7, 8, 9, 11 versus 4, 6, 8, 10, and 12. So notice that this goes just a little bit, they both have 8 as the middle value, but this stretches to 4 and 12, whereas this is 5 and 7. Set 2 should have a bigger spread than set 1. So I'd expect set 2 to have the larger standard deviation since, wow, that's a lot of choices. Okay, there we go. Some numbers in set 2 are farther from the mean than those in set 1 are from its mean, right? In other words, see this 6 is farther away than 7, and we would say that the 4 is farther away than the 5. In row A, the standard deviation for set 1, okay, so here's how we find that standard deviation. So let's write. So my standard deviation for set 1 here, by the way, I first need the mean. So to get the mean, which we notate X bar for the mean, I'm going to add 5 plus 7 plus 8 plus 9 plus 11 and divide by the 5 numbers that are there. So that's 12, 20, 29, 39, 40 over 5, or the middle number, 8, right? So my mean is 8. So now to get the standard deviation, I do the square root of the data point 5 minus its mean, 8, and square that result. Then 7 minus 5, 8 is the mean. 7 minus 8 squared, and then 8 minus 8 squared, and then 9 minus 8 squared, and then add on 11 minus 8 squared. All over, the number in the problem is 5 minus 1. So I'm gonna calculate all of this. I'm gonna put that in my calculator, and that's gonna be my standard deviation. Now, let me show you how to do it on the calculator. And for this, I'm gonna pause and bring up my calculator. Okay, so now I've got the calculator up. So the way that I can do this in my calculator is I can enter this in my list. So I'm gonna go to Stat, Edit, and in list 1 here, I'm gonna enter 5, 7, 8, 9, 11. And we're gonna go to the home screen, and then I'm gonna hit the Stat key and Calc, and the 1 variable statistics, option 1. On list 1, I want to make sure it says L1 there, since that's where I entered my list. And we get the standard deviation, 2.236. Now, notice this is the same that I'd get if I had done it by hand. By hand, I said to do parentheses for the numerator. 5 minus 8 is -3, and then square it, you get a 9. 7 minus 8 is a -1, and square it, you get a +1. 8 minus 8 is 0, square it, you get a 0. 9 minus 8 is 1, squared is 1. 11 minus 8 is 3, squared is 9. Close the numerator and divide by 5 minus 1 is 4. And when I enter that in here, I get 2.236. So I want to go to 2 decimal places. So 2.236 will round to 2.24. Now let's get the deviation for set 2. So I'm going to go back to my stat and edit, and I'm going to change these values to be 4, 6, 8, 10, and 12, and go into stat, calc, one variable statistics, and we get a standard deviation of 3.16. Without doing any calculations, all right, let's look at this. 5, 12, 13, 14, 21, 5, 7, 13, 19, 21. Okay, it looks like only a couple of the data points are closer here than they are here, right? So we would expect this to have the bigger standard deviation, set 1, since some numbers in set 1 are farther from the mean. Wait, did I say that right? No, set 2. In set 2, they're farther from the mean. So I want set 2 to have the larger standard deviation, because some numbers in set 2 are farther from the mean than those in set 1. Okay, let's actually calculate it. So we're going to go stat, edit, and in list 1, we're going to go 5, 12, 13, 14, 21. Whoops. And we get 5.70. And the standard deviation for set 2, we have 5, 7, 13. Whoops, messed that up. 5, 7, 13, 19, 21. And we get a standard deviation of 7.07. All right, now let's look at this one. 72, 75, 75, 78, 81, 87, 2, 5, 5, 8, 11, 17. All right, now notice that the center here seems to be the 8-ish on this one. And this is down by 6 units. So again, if I look at my center here, oh, my center. Nope, sorry. This isn't an even number, so that's not necessarily going to work out to be the mean. I'd have to add it up and divide by the number in that set to actually figure out what the mean was, unlike this one up here. All right, but notice that this is increasing by 3. This is increasing by 3. This is increasing by 0. This increases by 0. This increases by 3. This increases by 3. This increases by 3. This increases by 3. This increases by 6. This increases by 6. So even though the centers are different, the increase is the same from point to point. So I would expect both sets to have the same standard deviation. Now, why is that? Let's look for the right answer here. Both sets have, no. There we go. All numbers in set 1, are greater than those in set 2 by the same whole number. In row C, the standard deviation for set 1 is, okay, let's actually calculate it. Stat, edit, I'm going to plug in 72, 75, 75, 78, 81, and 87. And then I'm going to go to stat, calc, one variable statistics, and our standard deviation is 5.37. And we need to calculate it for the second set, but guess what? I already know it's 5.37 because it should be exactly the same as the first set. The histogram to the right shows the distribution of prices of plain pizza for 292 weeks in a large city. Is the mean closer to 283 or 320? Okay, let's look at it. So my mean should kind of be right about here-ish, right? Notice this data is almost symmetric. So right about the middle, now notice that 280s over here, that's wrong. 3 is right here in the middle. 320 is over here, that's wrong. So we're going to choose $3. And that's because it's where like the data balances. What's the standard deviation closer to? Okay. Well, notice that the bulk of the data seems to lie right in, like this is 1 block away, 2 blocks away, 3 blocks away. So I'm going to estimate somewhere in here, which is a dime to 15 cents-ish, is where we would have one grouping. If I do 50 cents would take me all the way out here. That's going way farther than one data. And then $1 is even farther. So it's got to be closer to the 15 cents, since that's a typical distance from the mean. The accompanying histogram shows the running times in minutes of the 150 top grossing feature films released in a certain year. Student plans to see a movie this weekend. Based on the movies, how long would a typical movie be expected to run? There's our running time. Notice that the bulk of the data is right in here, right? So now when I say the bulk of the data, I don't just mean the highest peak. I mean, there's about half the data over here and about half the data over here. The balancing point is right in around here. So 120 is too far. 75 is nowhere near enough. 140, too far. So it must be 105 minutes. Would it be surprising to find that the student's movie ran for 2.5 hours, 150 minutes? So here's 150, what did I hear? Well, would that be surprising? Notice that's a little bit on the long side. There's not much to the right of it, right? So I'm going to say most of the movies in the distribution, only a small number of movies in the distribution ran for 150 minutes or more. Would the mean or median runtime be higher? So if we look at this, notice that for this guy, drawing in my distribution, looks something like that. This is fairly close to symmetric, right? So I'm going to expect the mean and the median to be roughly about equal, because I'm dealing with something that's relatively close to symmetric. So let's try this first. Okay. A study looked at the running times of certain movies released in 2005 as shown to the right. The standard deviation of these is 19.6 minutes, and here are quartiles. Describe the spread based on the quartiles. Okay. So the middle, now notice Q1 to Q3, that first and third quartile, describe the in our box plot, right? No, I need a picture. In our box plot, this is Q1 and this is Q3. And this is the spread of the middle 50% of the data. So I would say, since they gave me the values for Q1 and Q3 here, the middle 50% of the data is in those two values. On average, movie links varied from the, okay, so notice it says the standard deviation is the 19.6 minutes. Standard deviation is variation from the mean. Since the distribution appears to be, okay, so what have we got here? If I look at this distribution again, it's not quite symmetric, but it's not super badly skewed either. So we're going to say that this is relatively close to symmetric. There would not be concerns about using these descriptions. For these data, wait, neither description is misleading. There we go. A clerk entering salary data into a company spreadsheet accidentally put an extra zero in the boss's salary, listing it this way. Okay. Explain how this error will affect the summary statistics. So I want to know about the mean and the median. Now, remember, the median is the middle 50%. If the boss's salary, he's probably already the highest. So arranging the data from small to high, right? My median is the point in the middle. If I make the high bigger, that doesn't change the point in the middle. So the median will stay the same, right? But the mean is the average of all these values. So if I average in a higher value, the mean will go up, right? So let's see where that's. The median will be the same and the mean will be too large. Option C. Now let's do this, the range. Okay. Now remember, with the IQR is the distance between the quartiles. So it's probably going to be unaffected, right? So my IQR is likely to be the same. Now, the range, though, is the distance from small to high. So that would get bigger. So the range would likely be too large. And the standard deviation is the deviation from the mean. This data point drags that higher. So the standard deviation will be too large. A survey of 12 gas stations produced the following prices for a gallon of regular gasoline. We want to do a stem and leaf plot. Okay, so all of these start at 2. Okay, so we're going to do 2.2 to 2.0. How many 2.26 do I have? All right, so I've got 2.03 means 2.30 to 2.039. All right, so we've got one of those. We see that here and here. Now, do I have a 2.0? They've really organized this one a little bit confusing. Let's see. So 2.059. So there's no 2.2. Okay, so you're using the first digit to represent all zeros to nines. Okay, there we go. All right, so 2.039 and 2.059. And then 2.069, 2.089, and another 2.089. So notice those are all represented here in this one. So this point right here, let's go, 2.08 is this point. This point right here is this point. The 6 is this point, and the 5 is this point. And then below it, the 1 and the 3, 2.019 is this point, and then the 2.039 is this point, right? And then 2.1, we've got 1, 2, and 3, 1, 2, and 3. And then the 2.1, we've got 6 and 9, 6 and 9, and then nothing in the lower half for 2.2, but we have a 2.69, which is right there. So option A should be our choice because it's the only one that matches up all of those points that were given. That's the difficult to read stem and leaf plot, right? All right, now let's look at the shape, center, and spread of the distribution. So notice that this seems to be a little bit skewed. It's skewed to the higher values. So that would be skewed right because that point that's pulling it up is kind of away from the other values that are there. The prices seem to be centered around, okay, so let's look for the middle value. 1, 2, 3, so there's 2, 4, 6, 8, 10, 12 points, so about the sixth one. 1, 2, 3, 4, 5, 6. So somewhere in between 2.0 and 2.1, right? So around 2.1. And then notice, by the way, I guess I didn't explain well there. What I was doing is I was locating the median, the middle value when I counted up 6. So our lowest prices are this, the 2.01 that's here. So let's find it. 2.01, 2.019. And the highest is that 2.26. So 2.269, this value. What unusual feature do you see? Okay, so nobody charged between 2 and 2.26, right? So we have that hole there. And that's in between 2.20 and 2.26. Okay, guys, we're almost done. We're on the last one. An internet company that sells piercing jewelry keeps transaction records on its sales. At a recent sales meetings, one of the staff presented the accompanying histogram of the postal codes of the last 500 customers so that the staff might understand where the sales are coming from. Comment on the usefulness and appropriateness of the display. All right, so let's see. This is our display. Now, these are my postal codes. So I can see, right, we've got a large bulk here, right? But what is this really telling me? This is telling me the number of people in each of these postal codes, that this is arranged on a continuum like it's meaningful, but a postal code is kind of just a label, so it doesn't mean anything. So the label is a categorical, right? A histogram should not be constructed using categorical variables. So a bar chart or a pie chart would be more appropriate. Is that it? Okay, that question is complete. All right, guys. So we've completed all of the homework other than those media questions you need to jump on, right? So we got all, oh, wait, I didn't finish 12? I thought I did. Yeah, I did. Okay. So you just need to look at these videos and then work your homework and email me. Let me know if you have any questions on what we've discussed.